Good morning. I am Krishna Kumar from Krishna's Classroom. We continue with our discussions on Riemann integration. In fact, this is the 10th part of it. What did we do so far? That is what we did in the last lecture. We looked at the problem of Riemann integrability. So essentially the problem is, can you characterize Riemann integrable functions? Now we looked at, so we found that from our experience we found that it is essentially the nature of the discontinuities of the function that play an important role on the Riemann integral. And we can afford to have a large set of points where the function is discontinuous, but it cannot be too large. And this is what we observe. In fact, we explored this problem a bit further and said that if f is bounded on the interval AB, Riemann integrable, then the set of discontinuities can be packed into a countable collection of intervals whose total distance can be made as small as we please. This is what we do. Okay? Right? So Riemann integrable functions can have discontinuities, and such discontinuities can be packed into the union of a countable collection of intervals whose total length can be made as small as we please. Can be made arbitrarily small. Now this is the consequence of Riemann integral. The question now we want to ask is, does this property of the discontinuity, the set of discontinuities, assure you Riemann integrability for bounded real valued functions on the interval A? This is the central question that we are going to explore. And if we are successful in proving that result, it seems to be eminently possible, we would have got a characterization. The characterization of the function will be, of such Riemann integrable functions, will be done in terms of the in terms of the nature of the set of discontinuities. Very beautiful theorem that you get. So let us explore this further. So before that, we introduce several definitions in the wake of what we have done earlier. So we defined what is called a null set. So we give some name for such sets. A set of discontinuities which can be packed into a countable union of intervals of total length less than epsilon for any arbitrary chosen epsilon. Of course, depending on the epsilon, you will have to choose the intervals. That's obvious. And such sets we give a name. So we define the following: a subset E is said to be a null set. We call this null set. Null set if given epsilon positive, there exists a countable family of intervals say we designate it as IN such that two things are there. One, E can be packed inside union of N and the length of the total length of the intervals lambda of IN is less than. If it is possible, then you call this a null set. Therefore, what we have proved so far is this. That is, we have shown that if f is a bounded function Riemann integrable, then the set of discontinuities is a null set. Set of discontinuities of f is a null set. Now this is the result that we have already proved. What we are looking forward to is to prove a converse of this. But before that, let us have some feeling for the null sets, like some examples for null sets, etc. Okay. So first remark I want to make is these ij's are intervals. Need not be restricted to open intervals or closed intervals, or closed at one end and open at the other. All sorts of intervals are acceptable. Not necessarily. Open or closed or open at one end and closed at the other. We are just intervals. You can have any sort of intervals. Now we look at some examples. As I said, the examples. First thing that you observe is that every singleton element constitutes a null set. 1 every singleton is a null set. This is quite easy to prove because X belongs to the closed interval X at length of Q. That is, if you want, you can use this notation, the notation that we have last time of this. See. Now, in fact, you can extend this to any finite set of points. So, any set of any set consisting of finitely many points, or any finite set. More generally, you can show that any countably infinite set what to do. So this is let countable set. What we do is we can choose ij the interval, even open interval, minus epsilon divided by u of u plus 1. This is true for j equal to 1 to. That's the definition of everything. Then you see that then S is contained in union and you also have sigma j running from 1 to infinity lambda ij. Therefore, S is a null set. You recall we talked about monotone functions on the interval AB. Not necessarily continuous. Then we made a remark that the set of discontinuities are countable. It can be proved using the property of monotonicity of the function. And then it comes out that the set of discontinuities of monotone functions form a null set. And that function was Riemann integral. That's what we proved earlier. So you take Q. Q is a null set. because it consists of countably many elements, and you can apply the above result and then you get the, I'm sure that it's an answer. Now, clearly, every subset of null set is a null set. This is obvious. Let null sets then union now apply the definition and one can get it easy. It's not difficult and sort of combination of this kind of ideas with several institutions. Now if you have a set which has only finite number of limit points, then E is a null set. If now here I think it's D. This is the trying to pattern. So this is your energy. Let a finite set of accumulation points. That E is a null set. Need some work, because all that you do is there are only finitely many accumulation points. You just isolate them using some open intervals, arbitraries of arbitraries. The length you can adjust. Then you see that what is left out would be just a finite set of points, which you can easily manage. Now one more thing is that let E contain in R null set. Then for x belonging to R, E plus x E plus x is essentially defined as, just recall, these are the definitions of E plus x and x. So one can verify that they are also null sets. One is of course translation of the set E, and the other one is scaling of the set E. Either stretching it or elongating it or contracting it. Okay. So the property of being a null set is invariant under these two transformations. Now you see that if I is an interval, having at least two distinct points, then E is not a null set. If E contains an interval, then E is not a set. All these statements do require a proof. Now there is a question that you can ask. If E contained in R is not a null set, does this imply that there exists an interval I contained in E? Now, this is the question that you can ask. You see that this is not necessarily true. Why it is not necessarily true? Because you look at the set of all irrationals. Okay? Consider the set of all irrationals. So you take or take E to be two complement intersection no. Now you know that this is not a null set. Needs some little bit of argument. It's not a null set. But this does not contain any interval. See, the set of rationals form a null set, but the set of irrationals do not form a null set. Okay? Right? Because if you were to pack it in a set of intervals, then it is going to be the length of the total length is going to be greater than 1, greater than or equal to 1. That's the reason. You cannot pack it as a countable collection of intervals which total length can be made arbitrarily small. That's the problem.